I'm Antonio Sala, and in this video we will continue with the case study about designing a force estimator with modeling errors. In a first video we discussed the LFT uncertainty modeling phase. In this video we will build the generalized plant and will carry out H2, H-infinity and mu-synthesis optimization. Performance comparison in time and frequency domains will be left for a forthcoming video for brevity. This was our nominal model, but the coefficient multiplying S is actually uncertain, and the force F, which we want to estimate, is assumed to be a band-limited one, being F the output of an all-pass or white noise input when filtered through a first-order filter with this transfer function. Our uncertainty in the damping could be expressed in this block diagram form, with this delta 1 normalized between -1 and 1 real parametric uncertainty, and the state space representation of the LTI subsystem was this GS1 in Matlab code, so in LFT with this delta uncertainty block gave me a robust control toolbox object describing a linear plant with parametric uncertainty. This was the uncertain step response. And for instance, if we analyzed the plant's stability margin, it says 1.81, which means that if I multiply the 0.55 uncertainty by 1.81, I get 1. So indeed, if this thing gets 1.81 times bigger, then this uncertainty would be able to swallow this -1 friction and touch the zero damping, the stability limit. So this is the meaning of this robust stability margin of my plant. In robust control design, we are interested in this margin in closed loop. In here, as we are designing state observers, the closed loop margins, let's say, will not change because we are not closing any actual loop. We will introduce some process noise and measurement noise parameters. Those weights will be incorporated to the weighted generalized plant. This process noise parameter 4 will tell me that this W has 4 squared as the power spectral density constant at all frequencies, white noise, if I am doing H2 optimization, or that it has a worst case amplitude of 4 if I am doing H-infinity optimization. And then I will have some measurement noise that will corrupt my position measurement, and the worst case amplitude or square root of power spectral density will be 0.25. You can download the code and play with these numbers if so wished. So we'll now discuss building the generalized plant the H2, H-infinity and mu-synthesis solvers need. I mean, they need a weighted generalized plant, but in control engineering we usually divide that problem into two subproblems. First, discussing the flux of information in a generalized plant, and then adding information on the amplitude of the signals to conform a weighted generalized plant. This weighted versus unweighted is irrelevant to the optimizer because they want the weighted stuff. And in fact, I am now putting in this diagram the noise amplitudes in here, but maybe you would consider them to be part of the weighted generalized plant, because why not? Okay, it's the same, only the end is what matters for the optimizers. So let us discuss the meaning of this block diagram, which poses our problem of state estimation, and will later on add on further weights. What does this block diagram mean? Well, it means that we'll have scaled amplitude 1 or power spectral density 1 process noise input that will be modulated to some physical units. In this case, multiplied by 4. It will be low pass filtered. This will give me the force that added to my U will move my mechanical system, and then I will have some position measurement in this case labeled as Y clean that will be corrupted with additive measurement noise V that again we will assume to be generated by an scaled unit power spectral density or unit amplitude V scaled that multiplied by this constant will give me the actual measurement noise signal. And this corrupted signal will be the measurement that will be fed to my observer jointly with the known input U. Then my task will be outputting some estimated state to be compared with the 3 state variables of my system here, which are the position velocity and this force, because it is the state variable of this low pass filter. So reducing this estimation error defines an observation problem. But okay, in our case, we will restrict to estimating a force and we will output just the force, so it's sort of short circuit here because it's actually an input to the second order system. So we will concentrate on minimizing this force estimation error. Then with suitable weights, if we have here a nominal plant with no uncertainty, we can carry out H2 or H infinity optimization. Or if we have some delta here, we can apply scale small gain and mu synthesis. We'll do all these options and we'll compare them later on. So this is the block diagram setting we are considering. And in order to express this block diagram thing, we will add a sensor noise addition block, this sum block, expressing this equation, and also an estimation error block, this sum block, which I named ERS3. Maybe it's a bit unfortunate name, but okay, that's what got into the code. So with those two summations, and using the connect command so that we connect signals by name, as in the above block diagram, we connect the uncertain system we already discussed in the first video, and this sensor noise and ERS3 summation blocks. And we request this generalized plant to have 4 inputs, this U, W, V, and the estimated force, because these constant blocks here will be part of the weighted generalized plant. So we forget about them for the moment being. And once we have those 4 inputs, we'll require also to have 3 outputs, the estimated error, the known input U, and the position measurement Y measured. And this is what we are telling the optimizer here. So we crafted the above block diagram as a robust control object called gen plant, generalized plant. And you can check whatever combinations of input and outputs to check that they fit what you expect. So we'll now discuss weighted generalized plants and optimal controllers. Our first design will be the H2 observer. In a plant without uncertainty, this is deeply related to Kalman filter and the like. So I will have a diagonal matrix with 3 elements in the diagonal being 1 and the process noise weight and the measurement noise weight. So I am now incorporating this thing so that there is a 1:4 ratio between F and U at low frequencies. This is 1, this is 4, and then this is small measurement noise. So I am putting those constants there in this weight input 1, and then the whole weight input is adding an extra unity thing that multiplies my estimated force, because in the LFT, the information to the controller, or to the observer in this case, and the controller output do not have any weights. They have, physical sense and interpretation. And then in the H2 synthesis, we will not put any output weight. So we are sort of computing a minimum variance, let's say, of the estimation error. Then my generalized planned nominal value times this input weight will be this PG numWin variable. I was not inspired with fancy names, I guess. So that the open loop standard deviation of the force I am going to estimate will be 1.8, and then hopefully my H2 observer will reduce that. If I do the H2 syn, then the observation error from not estimating anything with a standard deviation of 1.8 will reduce to 0.9 standard deviation of the observation error. So that's what my H2 observer does. My 002 has one output, estimated force, and two inputs, U and the measurement. So this is the H2 design for the nominal model we are discussing here. Let us now go with the H infinity design. In H infinity, we will add some output frequency weights. Okay, we could have added them in the H2 design to shape the power spectral density of the estimation error. So I leave it to you if you wish. We will indeed do that in the H infinity result. And these weights will be also shared with the mu synthesis option. So in here, I will define two templates which will be understood as the peak limits of my error amplitude in a worst case setting. I will have a high frequency limitation template 1 and the low frequency limitation template 2. So if I carry out the magnitude both plot, we can see here the low frequency template in red, the high frequency template in blue, and the open loop worst case amplitude of my force variable, the bow diagram of the low pass filter times 4. And so my H infinity and mu synthesis goal will be that the worst case amplitude of my force estimation error is below the minimum of these two templates. So below, say, this red stuff depicting the minimum of those two templates. So good. Minimum is a nonlinear operation, so we will do an output augmentation or lifting in the following sense. The estimation error will be sent to a filter 1 and filter 2 being the filter, the inverse of the template. Then I will get two weighted errors. So if this signal is below 1, then it means that this signal divided by template 1 is below 1, so this signal is below the maximum defined by template 1. And again, if f2 is the inverse of template 2, then this signal will be below the maximum defined by template 2. And well, this signal is the estimation error, so for sure, if both these things are below 1, then the estimation error will be below both templates. That's the basic idea. And of course, by stacking this, if I name A this signal and B this one, then if its norm is less than 1, then each of them will be less than 1 and the error will be below the templates. So this will be the output augmentation trick to have a complicated template constituted by the minimum of two simple ones. How do we do it in Matlab? Well, filters are the inverse of the template, and then the output weight, and will be a column with those two filters. So this will be a non-square matrix with 3 input signals, last 2 multiplied by 1, and the first one augmented to 4 outputs with this filter stuff. Once I have this, with the same generalized plant and input weight as the H2, then I will get weighted generalized plant that encodes the problem as I wish. And the outputs of that generalized plant will be the weight 1 of the estimated error, the weight 2 of the estimated error, and then the 2 inputs to the observer. And of course, if I get the nominal value, the 2 error weights with respect to the second input, which is the force, then this 26 as infinity norm in open loop tells me that at some frequency we are exceeding our template in a factor of 26, which is indeed what is happening at these low frequencies. So our H infinity or mu synthesis stuff will need to optimize for that. Once we have this weighted generalized plant, well then if we carry out H infinity synthesis, we get a gamma of 0.76, so we are below the template. But of course this is nominal performance of this observer infinity, OOI. These are the inputs and outputs. But if we get the worst case performance of the H infinity stuff, the stability margin, as this is an observer, it's just identical to the open loop one because we are not controlling anything. It's irrelevant in observer design. And what is important is the worst case gain. H infinity was designed with the nominal value, but when I plug in uncertainty, then the weighted plant has a worst case gain of 2.3. So I have very good nominal performance, 20% below what I required, but I don't have robust performance because gain exceeds 1 in a factor of 2.33. I only achieve performance in the limits I fixed if uncertainty is 37% of what it actually is in my model. So no way. If I do mu synthesis with the same weights and same generalized plant, musyn command, activating this stuff because I have real parametric uncertainty, then after some 4 point something seconds, I get a 0.999 robust performance margin. So this thing indeed does achieve robust performance. When I closed the weighted generalized plant with this observer mu synthesis, 9999 is the upper bound on the closed loop performance because, okay, I fiddled with the weights to get 1 here. Of course, the inputs and outputs of the mu synthesis observer are exactly the same as in the others, but do realize that order of the system due to the multipliers it's using inside is order 23. So it achieves the best robust performance results, but it doesn't have the order of the plant. So this is not an observer in which we have an internal copy of the state of my system as we have in the pole placement stuff. In here, we just have a huge linear system so that its output suitably resembles the true force. For brevity, we will finish the video here, and analysis in time and frequency domain will be done in a sequel video. If we summarized, in this video, we discussed the meaning of this generalized plant. We used constant weights for H2 and frequency-dependent weights for mu synthesis and H infinity synthesis. And we were able to execute the 3 optimizers to get 3 different observers. So the only remaining thing in next video is to compare them, both in robustness, margin, norms and whatever, and in time and frequency simulations. So we finish here. Thanks for watching.